Okay, I'm back on that black holes and general relativity lab. I had to stop so that I'm continuing where we left off with the Einstein ring. So let's say we have clicked on several parts and we have started accumulating data. So after you do this, 5 snapshots for each one, 1, 2, 3, 4, 5, then it's going to average them for you. Then you're going to go over here, and then there's a calculate the lens mass. There's a lens mass calculator, and then there's a redshift and distance calculator. So then let's go to the exercise, and you're going to be using all of these calculators. So now it says using the Einstein ring simulation above to discover the Einstein angle for the simulated example of a gravitational lensing. Then use the lens mass calculator to determine the mass of the lensing object. Record your results in the data table. So the lens distance. So how do we calculate the distance to the lens? So that means we are calculating the distance from us. So this is us right here. This is the Earth. This is the galaxy, or it could even be a black hole, supermassive black hole that's causing the background source's light to bend, you see? So we want to calculate the distance to that galaxy. So we're going to use the redshift of that galaxy. Z is 1.02, 1.02. Then we're going to go down here into the redshift and then put this as 1.02. The Hubble parameter, well, it depends all on the Hubble parameter, what the Hubble constant is, and the deceleration parameter. So the result, when we go and say calculate here, let's see here. When we put in all these results, and okay. So when I say calculate, it's going to give me the velocity of that galaxy, the distance of that galaxy from us in light years and in parsecs, and the fractional age of the universe when that galaxy's light was emitted. So, but it all depends on the Hubble constant. If I put the Hubble constant as 70, then say calculate, the numbers change slightly. And if I put the deceleration parameter different and say calculate, that also changes the results. So from all the data that we have, the deceleration parameter of the universe right now is -12. That means actually the universe is accelerating. And then the Hubble constant, let's look up the best value of the Hubble constant. Hubble constant is going to be about, it always varies our results for the Hubble constant, but right now it's about 70 kilometers per megaparsec. That's the present value of the Hubble constant, but some places they say 73, some places they say 70. So that's going to be, let's just say the Hubble constant is 70. So then we'll put here 70. I think it will, there's probably be a range of values where this program will accept it. So let's say Hubble constant is 70. The deceleration parameter of universe, a value of t greater than, okay, deceleration parameter is known as the letter Q. So the big long equations for it, but the deceleration parameter is -12 right now, the present value, which literally means that the universe is not actually decelerating, but it's actually accelerating. We live in an accelerating universe. But unfortunately, here, they don't give us a negative option for the deceleration parameter. So we could use deceleration 0, which means the universe is expanding at a constant rate. That would be a deceleration parameter of 0. If it's deceleration parameter is a half, that means the universe is slowing down at a certain factor. And then the greater deceleration parameter, the more the universe is slowing down. So I would say let's try deceleration parameter 0, Hubble constant 70, redshift 1.02, and then say calculate. The distance to that is going to be 3.244 times 10 to the 9th parsecs. Okay, so then you would take a picture of this, take a picture of that, and then take that parsec number, 3.244, and then put it into here. Lens distance, 3.2, what was it? 44 e to the 9th. 44 e to the 9th. Okay? And then you would do the same thing now for the source distance. So then you would go here. The source would be, in this case, it's 2.03 z. So then you would put that there. So let's say it's 2.03 z. Calculate, so it should be further away. Yeah, then it's 5.742 e to the 9th. Okay, then what was my Einstein angle? That means the angle of that ring that it creates, right? Due to the gravitational lensing. So let's say my average value, I'm just going to rough ball it. Let's say 1.01, 1.06, 1.0. So remember, you're clicking from the innermost to the outermost and then taking its average. So then let's say it's 1.07, okay, angle. Okay. 1.07 arc seconds. Now the lens mass, that one, the lens mass indicator will tell us that. You put here the lens distance. Oh, so then you take the distance here, 3.244 e to the 9th. 3.244 e to the times. Oh, it won't accept anything. 3.244 e to the 9th. No, it's not accepting scientific notation, so I'm just going to have to put zeros. 3244. Move the decimal 9 places over, so that creates 6 zeros. Right? Then the source distance would be this one, 5.742, 5742, which is also the one that I have here showing. Einstein angle, let's say 1.08 arc seconds. Okay, then he calculates the lens mass. That means the mass of that galaxy that's doing the lensing is going to be 1.06 times 10 to the 12th. That's a trillion. So that galaxy is trillion times heavier than the mass of the sun. Imagine how heavy that is. That means its gravity is so strong that it's able to bend that light and create an arc that is 1.01 arc seconds. So of course the idea is that the bigger the arc second arc is, let's say it would create at 1.45, the mass would be bigger, right? Oh yeah, then the mass of that, what if it's 3.55 arc seconds? That kind of a large arc, you would need a very strong, heavy galaxy. You see, it's 1.15 times 10 to the 13. So that means 11.5 billion solar masses. You see, so the heavier the galaxy in between us and the other galaxy, the more you can curve it, and therefore it looks bigger. The arc looks bigger. So let's go back to the original one, 1.08. Calculate. So then I'm just going to put 1.067 e to the 12th. 1.067 e to the 12th. And let's say how much it accepts. While the angular size of the ring suggests the mass of the lensing object, the mass scales as the square of the Einstein angle. The ring's size is also heavily dependent on the distances from the observer to the source object and the lens itself. So I guess we could try one more time. Now, what else can we change? We could change the Hubble constant that the app is using. I wonder if they're using 73. Because the Hubble constant ranges between 70 and 73. Let's say 73. Then that changes that distance. Does it change it? Calculate? Oh, it does change it. The distance is 5.462. 5.462. Try another. Oh, you got to put them all in. So 1.08. Oh, so hold on. What did it say? 5.462. And then we have to put that back into the lens calculator. 5.462. Imagine the distances of these things. And then you've got, then we get to then we got to go back to here and then do the previous redshift, which was 1.02. Now those numbers aren't changing. Those are given by the simulation, 1.02. It's called the redshift value, 1.02. Okay, so now calculate. So the distance is, hold on, so redshift 1.02. Oh, there you go. So 3.111 e to the 9. Okay, but now I got to put the new lens mass. Calculate. Okay, changed it slightly. I'm using the same Einstein angle. So then 1.034 e to the 12. Now, another error could be that I haven't done these very detailed, and I haven't done it 5 times and taken the average, and I'm just rough bowling the angle. So that could also be causing slight error in the angle, and which is causing the slight error in the mass. So let's say here 1.034 e to the 12. (1.034 e to the 12). Okay, let's see. Oh my gosh. Yeah. So we don't really know. I guess maybe they might be using a certain deceleration parameter other than 0, but then we wouldn't know. Because that's also going to change the distance. But if you try twice and you're still not accepting the answer, then that's fine. Just go with your last result and then take a picture of that, because that's kind of the unknown here, that we don't know what the app is using. So take a picture of this. Of course, take a picture of this one that it gave you, depending on which Hubble constant. In other words, whichever one you want to show here, whichever one you want to show, based on that, show the picture that you took, the snapshot that you took for that one. So if it was 73, then show that one. Then show another one with the other Z. So 2 pictures of this, and then 2 snapshots of that. I mean, no, 1 snapshot of that, and then 5 snapshots of this showing the result here, and as you accumulated them, and the average. Okay, so that one will do that. Now, what the next question? Oh no, there's no other question here. So now we move on to the next thing. Okay, now gravity waves. Okay, so small distortions in space. Gravity waves are spreading oscillations in the gravitational field due to the acceleration of masses. The gravitational waves is such a huge thing, and we had a revolution in 2017 when the first gravitational waves were actually detected using the LIGO. So that was one of the greatest discoveries of probably this century so far. There's been 2 great discoveries in this century. The Higgs boson, we discovered the Higgs particle around 2000, I believe, was it 12 or 13? And then gravitational waves were first detected in 2017, I think. So those were the greatest discoveries so far in this century. When charged particles are accelerated, they produce electromagnetic radiation. General relativity predicts something similar for gravity. Whenever an object with mass is accelerated through space, gravitational waves or gravity waves should be produced. These waves should travel at the speed of light and cause small distortions in the space through which they travel. Due to the relative weakness of gravitational waves, they have not yet been directly observed. Astronomers hope to detect gravity waves from astronomical phenomena in which very large masses are being accelerated, such as in the binary system of neutron stars and black holes. Over time, the orbits of these objects should decrease in size as energy escapes in the form of gravity waves, causing the components to orbit more rapidly. Just as the radio antenna generates radio waves from the movement of charged particles, the movement of matter causes gravity waves to radiate outward. This is a great analogy, actually. Just like electrons flowing up and down at a certain frequency, they can cause a radio wave to emanate, right? At whatever frequency of the radio station that you're listening to. So if it's KISS FM 102.7, then that would be 102.7 megahertz million. So that means the charged particles have to oscillate back and forth at 102.7 million cycles per second in order to produce the FM station KISS FM, right? So that means the same way as matter is accelerated through space, then it also creates gravitational ripples. Currently, there are several experiments searching for direct evidence of gravitational waves, such as the mini-Grail gravitational radiation antenna in Leiden in the Netherlands, LIGO laser interferometer gravitational waves in the United States, CLIO, cryogenic laser interferometer in Japan, and GEO in Germany, and the Virgo interferometer in Italy. So quite a lot. LIGO, well, LIGO is the one that did the observation. So I'm not sure if this was written before LIGO observed it, because they're saying no observations have been done yet. But yeah, the LIGO did observe it, but I haven't heard about the other ones observing gravitational waves. The one in Japan, Germany, and Italy. As of yet, none of these experiments have directly observed gravitational wave. An additional space observatory, LISA, Laser Interferometer Space Antenna, was recently canceled due to lack of funding. Okay, you see, funding is another huge disappointment in the sciences. When governments choose not to fund certain projects and it's left to private institutions, sometimes they don't have enough funding, and so it gets canceled. So LISA, I guess, was canceled. The binary pulsar. Binary pulsars are one opportunity to verify the existence of gravitational waves and to test predictions of general relativity. That means these are two pulsars rotating around each other, and we saw in the last lab that there are a lot of pulsars like that. Remember, they are binary pulsars, and even the pulsars that were in globular clusters, which are likely to have binary pairs. So since these guys will distort space so much, they will actually cause gravitational ripples. So in 1974, while using Arecibo radio telescope to observe the pulsar, PSR 1913+16 made an important discovery with implications for general relativity. Unlike most pulsars that have very regular pulses, the pulses from PSR 1913 varied periodically over several hours. Objects in motion create gravitational waves. This is especially true of two massive objects in close orbit with one another. You see here? See how they're creating the ripples? Then they come closer, they create a huge ripple. When they're farther apart, the ripple that it's creating is less. So you're creating peaks and troughs in the wave, right? So this is a trough, then peak. Right when they get close, a new wave starts, you see? Look at that now, getting close. Right there, you see a new wave is starting. And then far apart, and then so on like that. Right there, yeah. The variation can be easily explained in terms of light travel time. If the pulsar is part of a binary system and orbits about the system's barycenter, which is another name for the center of mass, the pulses will arrive later when the pulsar is on the far side of the barycenter and will arrive sooner when it is on the near side. So that means when the pulsar is on here, you see, quickly creates a pulse. And then, so when the pulsars are farther away, they're moving slower, you see. And will arrive sooner. So while analyzing the shifts in the pulses from PSR, it was found that it and its companion both have masses around 1.4 times the mass of the sun. Also, each one individually had a mass around 1.4, which is actually, from what we learned earlier, that is the least mass that a neutron star can have, which is the heaviest mass that a white dwarf can have. You see that? So so individually they are both 1.4 solar masses. Since the companion cannot be seen and is so massive, it is most likely a neutron star. Even though we cannot detect pulses from this second object, the system has become known as a binary pulsar. Oh, so you see what's going on is one of these pulsars, the beams are pointing towards us. The other one, the beams are not pointing towards us. So it's a regular neutron star. You see, remember how we did that experiment with the beams facing us? So if one of these, the beam facing us, it becomes known as a pulsar. The other one is a neutron star. But they're still both pulsars, but only one of the beams is visible. So in other words, we discovered the other neutron star by its gravitational effect on the pulsar that we can see, you see. So this system, two massive objects in a tight orbit, allows a unique opportunity to test the predictions of general relativity. Two of the most important predictions are that the orbits should precess in space, that is, the semi-major axis should rotate, and that the orbit should decay in size as the system emits gravitational waves. So remember that we saw that video that it was showing us the precession, kind of like how Mercury's orbit precesses. And so there are two observations we are testing that from this simulation. One is the precession, and one is the gravitational waves. So this lab allows you to explore the aspects of a binary pulsar in which two pulsars are in orbit around each other. There are 3 timescales that reflect the durations of different aspects of the system. In the milliseconds timescale, we see one of the pulsars shining its beam towards us as it rotates. In the hours timescale, we see the 2 pulsars in orbit around each other. In the years timescale, we see the precession of the system due to the general relativity. Oh, beautiful. So depending on which time scale we click, we're seeing different events. In the millisecond time scale, we're seeing the pulsar, one of the pulsar's beam is shining towards us. In the hour, we're seeing them go around each other. And in the years, we're seeing the precession of the orbit. The speed of the simulation can be controlled in each time scale. Use the slider to set the timescale value. You can use stopwatch feature to time different aspects of the system. Press the button starts to stopwatch. Releasing the button stops it. The Periastron line connect the points where the pulsars are when they are closest to each other. So this is the periastron. You see, it connects the 2 lines when they're closest. You can use this line to more easily track the precession of the system. Check the show periastron line to the line box to see the periastron line. Okay, so let's examine here what's going on. Okay, so if I uncheck the periastron, that periastron goes away. Okay, now let's look at the millisecond time. Oh, okay. So you see only this pulsar is shining towards us. Boom, boom. Okay, so then we could time. Let's see here. Can we stop this? Oh, this one speeds it up. Oh, okay, millisecond. Oh, this one already measures for us the how many seconds it takes to milliseconds per second. Time scale selector, milliseconds per second. Okay, hold on. Hold up, let's zero it. Okay, for now, let's just observe it and not try to do any particular numbers, and then we'll see what they want us to do. So this one just speeds it up. Okay, so now let's look at the hour scale. Okay, so now speeding that up makes them go faster around each other. See that? So besides this top one spinning, it's also going around its companion pulsar. Okay, how about your scale? See, besides going around like this, their periastron is precessing, you see? And that's due to general relativity. Now, if they had another scale, like maybe, let's say, instead of years, let's say decades, we might see their orbits getting smaller and smaller. Why? Because as they emit gravitational waves, these orbits should be getting smaller and weaker, you see? So if they had a decade scale, that's what it could have shown. Not only precession, but it would have shown the orbits getting smaller and smaller and smaller over billions and billions of years, right? Because they're emitting gravitational waves. So I think I like this. You see, we're seeing all aspects. Then you're looking at the millisecond aspect. Yeah, okay. So now let's look here. So 3 questions based on that. Using the binary star simulator above, set the timescale to milliseconds and use the stopwatch to measure the period of the pulsar. It may help to use the slider on the timescale selector to slow the rotation down in order to more easily engage and release the stopwatch. So using the binary star simulator and use the stopwatch to measure the period of the pulsar. Slider on the timescale selector. Oh, okay. So basically it's saying you go like this. Oh, okay. So by changing the slider, what you're doing is basically like slowing the movie. So it's actually not changing the actual pulsation rate of the thing. All it's doing is that it's changing the framing of the movie. So now if I go like this, oh, okay, I guess here, let's do this. You know, let's go like this and go. Hold on. Every time, okay, yeah. Every time you start this, it starts back at 0. Okay, nice. Start. And then the next time it comes towards us, stop. 59.23 milliseconds. You see? Let's try that again. 1, 2. Okay, 61.29. You see, so you gotta get good at that. That's gonna give us the period of rotation of that pulsar. Okay. So 58.88. Okay. Now, if I go slower, is it gonna be easier to do the timing? Let's go. If I go slower, it might be easier. And you go like this. Yeah, I think that's better. Like if you go slower, you still get the same result because this isn't changing the actual the rotation rate, but it's easier to see when it's pointing towards us. So 59.58, let's see if it will accept that. Okay, nice. Okay, so basically we would need to take how many pictures here? We would slow it down. So when it comes towards us, oops, hold on. Right there. So then start the stopwatch, 0. So take a picture of that. So you're basically showing how you're doing your reading. You're doing your reading when this is pointing towards you. Let's enlarge this. You're doing your reading when this is pointing towards you. You see? And then you could go a little bit faster. Slightly. Okay. Oh, hold on. Didn't the thing start? Oh, hold on. I think I should have. Oh. So let me go back to when it was pointing towards us. There you go. Ah. Okay, let's make sure I'm outside of that. Oh my God. Why is it doing that? So take a picture of it. Why? Why is it on that? Oh, okay. I gotta make sure I click outside of that box. I'm technologically limited here. Okay. My God. Why is this so hard? This gives me such a hard time. Okay. Still thinks that I'm there. Ah, I see that. So I took the picture fine, but the problem was, hold on. Hmm. Maybe I need to, maybe the problem is I'm too zoomed in. Hold on, that might be the problem. Ah, okay, let's see. That might be the problem. God, now I'm afraid to go all the way to the left. Okay. Okay, maybe I was zoomed in. That was the problem. Okay, so this is one of the pictures. Then I start this. Oh, I gotta start this. Then go like that. Ah, it didn't start it. It needs to start the clock. Why isn't it starting the clock? This is tough. What I'm asking you guys to do is tough. Uh, oh my God. Hold on. What if I make it even smaller? Okay. Okay, take a picture of that and get this started. How do I know which one is the start? I think this one. No? Oh, that's not the start. No. How do you get this started? Oh, okay. What you know what you could do? After you start this back up, you don't have to do the very next cycle. You can let it go and then now get it started like this. Ready, go. Yeah, there you go. If it doesn't immediately start, you can always wait. There you go. And now take a, oh, hold on. That's not what I was meaning to do. Restart. Go. Okay. Now slow it down. No, hold on. In other words, slow it down and stop it. This is going to be a challenge. This is going to be a challenge. I want you to stop it when it's showing the 58 or the 59. So hold on. Let's see here. Okay, ready, set, go. No, go. Oh, this thing. Well, this thing, when you changed it, hold on. Okay. When you, well, I guess you can't stop it. The problem is when you try to slow it down. Okay, here's you're probably gonna have to take a picture with one hand and while stopping it with the other. Yeah, okay. So with my left hand, I can put the cursor, go. Okay, then with my other hand, I can take a picture once it completes one orbit. Ready, set, and picture. Okay. Oops. Didn't work. Ready, set, hold on, let's restart. 0. Ready, set, picture. Yeah, there you go. So I just started a little bit late. So you have to practice that a little bit. You take a picture while it's pointing at you and while this is showing 58. So those would be your two pictures. One while it's 0 pointing at you and one while it's whatever answer you got. And then that's the one you put there. Then question 2. Now use the binary pulsar simulator to determine the period of revolution of the system. Period of revolution in hours. Okay, so then you would go, oh, okay, then you would go to the hours. Oh, no, in hours. So how would you determine the period of revolution? Is this, okay, this one also had, so now we could slow it down. You know what, let me start out with, I don't like the way it's pointed. I like this one better. Okay, so then I could take a picture with, well, basically what we're going to do is start when they, let's go like this. So take a, I think this one should be easier than the other one. Take a picture when they're at a certain location, and then when they next reappear at that same exact rotation. So basically, you start out with the light blue one is there. I could go a little bit faster. Ready? Now you would take a picture with one hand and then press click with the other hand. Right here. Okay. I just don't want to change this while this is running because it might stop this. it might stop the stopwatch. So now I'm going to wait till it goes the full cycle. So remember, the light blue one started here and then goes around and comes back. So you wait till it comes back to exactly where the initial situation was. Okay, so now this is half a cycle. You see? So you wait till it makes a complete cycle now. This is an actual pulsar, I believe, that they're giving us an example for. The period of the pulsar was something like milliseconds, about 60 milliseconds. And it's a binary pair. They're going around every several hours. Okay, so now get ready for the picture. Right there. Okay, I think that should be good. So then that picture right there. So let's try that. And of course, you would just put it in and see if it accepts it. If it doesn't, who cares? Right. Let's see here. Then question 3. Finally, what is the length of one complete precession cycle for this binary pulsar? Hint, for this, it may be helpful to have the Periastron line displayed to keep track of the rotation. Length of one complete precession cycle. Okay, this is going to take a lot of years probably, huh? Let's see here, years. Okay, so let's start with you know what? I like starting it when it's vertical. I just got used to that. Okay, so now I'm going to slow it down. Okay, then get ready, take a picture. Ready? Oh, I passed it. Damn it. Okay, you know what? Let's go. Okay. So this is the Periastron Line. Technical words here. Okay, so I'm going to start it when the periastron is vertical. And then take a picture at the same time too. Ready, set, go. Okay. Wow, so it's already 2 years have passed. That means 2 Earth years in our time have passed. This is actually pretty fast precession. Mercury's precession is nowhere this fast. It takes thousands, millions of years, I think, for Mercury to precess once around. What is we could look it up in a second. What is Mercury's precession period? Now, has it gone around the full? You have to be careful now. Which one was which? Because we're not seeing them, did it? I forgot. Wait, did I even put the stopwatch? Why did the stopwatch stop? I didn't even click anything. Hold on. Let me just restart. Ready, set, go. So now I need to look at this one, keep an eye on that. It's got to go all the way, keep an eye on that end. It's got to go all the way there and then come back. If I look at the line, I might get, you know, I might get tricked. So I have to wait for this to go all the way around, come back all the way to the bottom. So, man, that's already about 21 years. So it looks like it might be about 80 years for the period. So then you would take two pictures again of it, the whole revolution. So it's still about to make half, then it's got to go all the way around and come back. And then based on that, you would give that answer. Okay, then show pictures of each of these as well. Okay, I think that's it for that part. Okay, binary pulsar. Now we go to nature of black holes. Oh, the fun topic, nature of black holes. So the Schwarzschild radius is the distance within which nothing, not even light, can escape from a black hole. The surface defined by the Schwarzschild radius is called the event horizon. While a black hole itself may be a point of infinite density, there's a region around the hole where anything that enters it is bound to fall into the black hole. Not even light can escape once it has crossed this critical boundary. The surface of this region is called the event horizon. From outside the event horizon, we can have no idea what is happening on the inside, hence the appropriate name, black hole. The location of a spherical black hole's event horizon is given by the Schwarzschild radius. The more massive a black hole, the larger its Schwarzschild radius. The formula for the Schwarzschild radius can be derived using the formula for escape velocity. V escape is equal to square root of 2gm over r. This is the general equation for the escape velocity that you need in order to escape any planet's surface or any star's surface. But the escape velocity from the event horizon of a black hole is equal to the speed of light c. So using that fact, the speed of light c, we can square both sides of this equation and come up with an equation for r. So we set the escape velocity to speed of light c, and then we solve for the radius to get the Schwarzschild radius. So you see this, when you square the square root, it gets rid of the radical sign, and then you get 2gm over c squared. This is a simple derivation. Remarkably, a derivation using the full power of general relativity also gives you the same result. Photon sphere. The photon sphere is the distance at which light can go into a circular orbit around the black hole. Where light can go into circular orbit around the black hole. At any closer distance, it is impossible for a massive object to orbit the black hole. Okay, so it's saying at any closer distance, it is impossible for a massive object to orbit a black hole. Light can go, so that means at the photon distance, light can actually go in a circular orbit around the black hole and not be trapped, not be sucked into the black hole. Another important quantity for a black hole is called the photon sphere. The photon sphere is defined to be the radius at which light can go into circular orbit around the black hole. It generally lies outside the event horizon. For a spherical black hole, the radius of the photon sphere lies at 1.5 times the Schwarzschild radius or event horizon. So you see that? It's an interesting photo. So a beam of light can come and traverse the black hole, and this is the event horizon. So it can go around complete circle. That's known as the photon sphere. And it's 1.5 times its, so if the distance from here to here, whatever that is, you're taking half of that and then adding it to it. And that's going to be the photon sphere. Black hole simulator. Okay, so here's another equation then. The simulator allows you to explore some of the basic properties of a black hole, which in this simulation is represented by a black circle at the center of the screen. So then I'm going to say, so when the mass So you could put any mass for the black hole in kilograms. Okay, so then remember, based on this equation, that the radius of the black hole, the Schwarzschild radius, is linearly proportional to the mass of the black hole. If I double the mass, the radius of the black hole will double. Triple the mass, the radius will triple. These other things, the 2g and the c squared, they're just constants. Wherever you go in the universe, they're constant. The only things I can change here, I can change the mass of the black hole and thereby calculate the Schwarzschild radius based on that. So then here I can give any mass. Let's put, for example, the mass of the sun to e to the 30th. That's approximate mass of the sun. What would the Schwarzschild radius of the sun be? If the sun were to turn into a black hole now, its Schwarzschild radius would be 2,970 meters. Its photon radius is 1.5 times that. You see that? That's awesome. Look how small that Schwarzschild radius is. That's only about 3 kilometers. See, 2,970 is about 3 kilometers. So that means the Schwarzschild radius of the sun would be actually inside of the sun's core. So that means the sun would never turn into a black hole. Its mass is too little. And its core would never collapse that much. So, I mean, we could go into the whole theory, but basically black hole, our sun cannot turn into a black hole. It's black. Even if it did, its Schwarzschild radius would be inside of it, you see. But now, if you get an object that's about 3 times the mass of the sun, or 2.5 to 3 times the mass of the sun, that could turn into a black hole. So 3 times mass of the sun would be about, okay, hold on. If the core of the parent star, so in other words, the original star that dies has to be pretty heavy, like 30, 40, 50 times the mass of the sun. But when its core is 3 times the mass of the sun, then that core will collapse. So you see here, the core means it's about 6 times e to the 30 kilogram. That's the lightest mass black hole you can have. Black hole, the core of the star has to be about 3 times the mass of the sun right there. Then that core is gonna shrink to almost nothing size, to almost nothing. It's called a singularity. And then the Schwarzschild radius for that will be about 9 kilometers. Yep. So the smallest black hole you can have there is about a 9 kilometer radius black hole. That's what we just proved right there. See, 8,911 is approximately 9,000. So that's about 9 kilometer black hole. That's the smallest black hole you can have because that's about the lightest black hole you can have. It's 3 times the mass of the sun. But now if you go to a lot heavier than the mass of the sun, like for example, the supermassive black holes at the centers of galaxies, they can be 1,000,000 times heavier than the sun. So this would be 2 e to the 36. So that black hole is exactly 1,000,000 times heavier than the sun. Exactly 1,000,000 times heavier. That's called a supermassive black hole. Its Schwarzschild radius will be 3, okay, let's convert that to kilometers by dividing by 1,000. So that'll be about 3 million kilometers. 3 million kilometers, yep. That black hole will just eat up anything close to it. 3 million kilometers Schwarzschild. Okay, so you see how that simulation works. Is this changing at all when I'm changing the masses? It's not getting bigger. Wait, what is this showing? Oh, is this showing like, okay. This is showing there you go, that's cool. Oh, I see. So it's showing the bending of light. when you go close to the black hole. You see? Ah, I like that. I like that. So it's saying here, laser instruction. The laser allows you to follow the path of a hypothetical photon in the proximity of a black hole. The laser can be moved and rotated to any point on the screen. To move the laser, click and hold the front half of the laser. Moving the mouse brings the laser along with it. Okay, so there you go. Right there. Then it says to rotate the laser. Moving the mouse now causes the laser to rotate its front end. Hands appear to indicate whether you're moving or rotating. How do you rotate here? Oh, there you go. Ha ha ha. Oh, okay. You can aim it at anything. You see, you're still not trapped. So each of these boxes are representing what? So it says, I enter a value in the mass field and the calculator will find the Schwarzschild radius that photons were. You can select either kilograms or solar mass. When a valid mass is entered, a scale bar appears in the lower right corner, giving the approximate scale if the black hole on the screen has that mass. Let's see here. So let's go to, we could even do this in terms of sun masses. Okay, so then that's even easier. We can say one solar mass, two solar mass, three solar mass. There you go. That's the lightest solar mass. Then 4, 5, 6, 7. Then what scale appears here? When a valid mass is entered, the scale bar appears in the lower right. Corner, giving the approximate scale if the black hole on the screen has that mass. Okay, hold on. Oh, it hasn't appeared because we haven't been able to find out. So in other words here, I have to get this closer and find out at which point my photon makes a perfect circle. Okay. There you go. So I'm going to have to do, it's almost like an experiment you're doing, I believe, right there. Yeah. So let's go like this and rotate it like this. I think it's easier if you're coming in horizontal. See how you're bending and going in? So no matter where I'm starting, the beam of light is coming and falling into the black hole. So now I'm going to start going further away. Okay, until I make a complete circle. Oh. Oh, nice. So now I'm safe. The bending of light. See how the bending of light is visible? God, this is amazing. This is how we proved general relativity in 1919, when the bending of light happened around the sun. But this is, we're talking bending of light around the black hole. So now I wanted to make a complete circle. I believe, oh, no, right. It doesn't look like a complete circle to me. Well, maybe it is. Okay, so let's just say something like, it's very, very sensitive to fine deviation because you got to get it just right. When I'm increasing this 2.5 radius of the photon meters. So I'm not sure what the scale on this is. Let's see what the instructions on the event horizon exercise is. Oh, okay, there's just one assignment. Okay, so it says use the black hole simulator above to calculate the Schwarzschild and Photon Sphere radii for the objects in the table below. Okay, so then you put the mass of the Earth, Schwarzschild radius, and the photon sphere. So then that one is easy because you can just take the whatever that would, you would put that in kilograms, put the mass of the Earth, whatever its Schwarzschild radius, you would put it here, the photon radius. So you would take one photo of that and a photon radius for the Earth. So photon radius for Earth would be what? Let's see if you had. So let's say something about the mass of Earth. I'm not going to use exactly the Earth's, but something similar to the Earth's. Oh, but the thing is, I think when you're changing these, it's not necessarily changing the mass of that black hole. Yeah, it's not changing. So this isn't really changing laser instructions. Hypothetical photon in the promising of black hole. The laser can meet to rotate. Moving the mouse now causes the laser to rotate around its front, and hands appear to indicate whether you're moving. Okay. Common instructions. Basic one. Schwarzschild radius. When a valid enter a value in the mass field and the calculator will find the Schwarzschild radius and photon sphere for that mass. You can select either mass is entered. A scale bar appears in the lower right corner, giving the approximate scale of the black hole on the screen has that mass. Okay, so then basically whatever the radius of the Schwarzschild, I was hoping that when I change the mass here, that actually that would allow me then to test the photon radius of the Earth, but I don't think it works that way. So you just change the mass and then it shows you here, and then you do the sun, then you do black hole at the center of our Milky Way, 4.3 million solar masses. Then you would put those and calculate these, and I think that would be it, really. That's all it's asking as far as this. Okay, but let's see here. I think if we do this correctly, almost. Okay, look, think about it this way. If this is the Schwarzschild radius, is the Yeah, that photon radius should be around there. Okay, if the gray one is the Schwarzschild radius, right, that's this one. Let's see here. I think in our case, they're showing the black hole is this. This one is a little bit different than this one. On this, the whole region is black. The black hole would be right in the center. And this is the event horizon. Okay, but in this simulation, this part that's black is the black hole, and the gray is the Schwarzschild radius, you see? Once I'm inside the Schwarzschild radius, I'm getting trapped. So now if I go 1.5 times farther away of the Schwarzschild radius, I should be able to achieve a perfect circle. Wow, this is hard. Get it really. Slight rotation. Trying to get a perfect circle. Maybe rotate a bit. Not quite. I wasn't able to get it. Okay, so from there, we can actually show, so that you could take one snapshot of that, zoom in on it. Oh, when I zoom in, everything changes, right? Need to go closer. Okay, so you should be able to show that whatever distance this is, you see from here to here, whatever distance that is, that's the Schwarzschild radius. Think of this as the singularity. The only reason they made it big is so that you can actually see it. But in reality, in a real black hole, this is a dot. It's just a dot. And then from here to here is the Schwarzschild radius, right? So now if you take 1.5 times that, so that means you would take half of it and you would add to it. And so the photon radius should be there. So we're trying to just show graphically that that does create almost a circle. If you can't get it to work, that's fine. I wasn't able to get it to work. I'm trying to complete the circle. Yeah, but it doesn't work. Almost a circle. So that's about 1.5, right? You can tell this is 1 and then this is 1.5. So then you take a picture of that showing that you got the photon radius to be about 1.5 times the Schwarzschild radius, which means a beam of light by definition would neither escape the black hole, neither would it fall into the black hole. It would be in a safe zone. So then you could take a snapshot of that. If it doesn't work, it doesn't work. It's tough. Okay, I think that's it for that section. Let me go to the next one. So black holes have no hair. That's interesting. Do they get haircuts a lot? So all of the distinguishing characteristics of matter are destroyed by a black hole, leaving only mass, charge, and angular momentum. So the reason why they say black holes have no hair is because you can distinguish people oftentimes by their facial features, and one thing that you can distinguish them by is their hair. You can tell them apart. So black hole has no hair. Hair is just a colloquial way of saying all black holes look the same, except their mass, which is going to be different. And then their mass is going to decide their size. If they have charge, it's going to decide a certain important characteristic of the black hole. And if they have angular momentum. So they only have three characteristics, things that can distinguish them. Mass, which will determine their size, of course, charge, and angular momentum. We now know how to calculate the region of influence surrounding the black hole, but how big is the object itself? Astronomers believe that the black hole has zero volume. Remember how I was saying that black dot is like zero? And refer to this as a singularity. Because all the mass is compacted into zero volume, a black hole is infinite density. An astronaut approaching a black hole would find the extreme tidal forces somewhat uncomfortable. Tremendous tidal forces exist near a black hole, which stretches any matter out and destroys its structure. As matter falls in, almost all the information associated with it is destroyed. The only quantities that have any meaning for black holes are their mass, angular momentum, and charge. So if you were to fall into a black hole, nothing about you would matter. What you've accomplished in life, how big you are, how small you are, all that matters is your mass. That's all. The black hole just would take that in, suck you, and the black hole would grow in size. Nothing else about you would matter. That's kind of interesting. The lab considers only black holes that lack any angular momentum or charge. So we're not going to worry about charge or angular momentum for this kind of black holes. We're not going to worry about their angular momentums. Astronomers jokingly refer to this by saying that black holes have no hair. Intriguingly, this line of thought has been challenged recently and continues to be an area of active research. Okay. Now we go to the detection of black holes. How do we detect them? It is difficult to detect black holes directly. Therefore, we look for their effects on their surroundings, such as a star orbiting a massive yet unseen companion. It is very difficult to detect black holes since light cannot escape from them. We must detect them from the indirect evidence that comes from the effect that they have on their environment. Thus, one could argue that the existence of black holes is not proven without a shadow of a doubt. However, there are many places in the universe where observations cannot be explained in any other simple way than by assuming that a black hole is present. So basically, we are inferring their existence, but we don't actually see one. This hot blue star is moving around an unseen companion. It is probably a white dwarf, a neutron star, or a black hole. So you see this companion star? Now, what is it rotating around? It might be rotating around the white dwarf, which we usually can see, but they're hard to see. Neutron stars also very, very hard to see, but if you give it enough time, we can still discover and see neutron stars. But black holes, we just infer their existence. It's probably the black hole is like somewhere around here. For example, suppose that you see a star orbiting as if it were part of a binary system, but with no visible companion. If you can establish from the motion of the visible star, then the unseen companion is more massive than the theoretical upper limit from a neutron star. Ah, see, that's the other thing you do. You can do calculation based on the mass of this guy, of the blue star, and the time it takes to orbit, how long it's taking it to orbit. Then you can complete the calculation for Kepler's law, find the combined mass of the two stars. And then from there, deduce the mass of that unknown object. If that unknown object is more massive than 2.5 solar masses, then it's a likely black hole. So that's one evidence, is indirect evidence by doing calculations on that unknown object. A more direct evidence would be like the accretion disks accumulated around black holes. So an accretion disk is a disk of rotating matter spiraling into a black hole. Often this disk gives off massive radiation. So this would be, we would call more direct evidence. Although a black hole itself may not emit any light, the area around the black hole may give off lots of radiation. As matter falls into a black hole, friction causes it to heat up to millions of degrees. And at such temperatures, it emits large amounts of X-rays. You see there? As the accretion disk is accumulating around the black hole, and the friction of those accretion is emitting huge amounts of X-rays and even gamma rays. So the X-ray produced by accretion disk is one way that we have for identifying black hole suspects. We know the black body curve for a hot star peaks in the ultraviolet. You see? Remember we did the black body curves before in another lab? And thus there are very few X-rays being produced. So if we see an unusual amount of X-rays coming from the direction of an otherwise normal-looking star, we interpret that star as belonging to a binary star system with a highly condensed object, which is likely to be neutron star or black hole. Gas from the outer atmosphere of the star falls into the condensed object, providing the source of material. Remember how we talked about the Roche lobe and one star feeding another star? If we can determine the mass of the unseen companion from its influence on the visible star, we may be able to determine what kind of object it is. And if the mass is greater than 2.5, then it's a black hole. If the mass is less than 2.5, then it would be a neutron star. So this could also provide way of detecting neutron stars as well, unseen neutron stars. Some black holes in binary systems have their orbits inclined along our line of sight, like an eclipsing binary system. Thus, the X-rays from the accretion disk are blocked. But when the black hole passes behind the star, we can form a light curve. Thus the X-rays from the accretion disk are blocked. But when the black hole passes behind the star, we can form a light curve from the X-ray intensity, which will help us learn about the parameters of the system. You see? So this is the black hole system simulator, which allows you to study the system by readings of the X-ray intensity. The meter shows the instantaneous X-ray intensity from a suspected black hole system. You see? So now, let me just minimize it a bit. So now it says, use the take measurement button below it to record this intensity measurement. Take special care to make measurements when the intensity dips. The statistics analysis on the next page uses these dips to estimate the period of the system. When the intensity seems constant, you don't need as many data points. After you have several measurements, 50 or so, go to the next page in this window to analyze your data. You can always come back to make more measurements. So basically what's happening is that the black hole is going around the star, and when the black hole is not hidden behind the star, we see the X-rays emitting, right? But when the black hole is hidden behind the star, that X-ray intensity dips a little bit, and then we can tell its period. So take measurement. Hold on. Let's go. This is the black hole system simulator. Which the curve at left is calculated by running a statistical analysis on the data you've taken. Oh, okay, come on. You know what? You gotta go to the left first. Oh, we took the data right there. We already took one data. I clicked. You see, so we took an intensity and the phase. So let's go back. Take measurement. 2 measurements. Oh, measurement. Oh, it's dipping. Let's see here. Okay, so measurement. Okay, that one's constant. Oh, dips. Oh, constant. Dips. Okay. You see? So then let's go to there and let's see how that fills it up. Okay. So you see the dips, slight dips in intensity. So zoom full. What does that do? Zoom full, submit, intensity. Okay, so here you're seeing each one is showing something different. The curve at left is calculated by running a statistical analysis on the data you've taken. Low values of theta indicate likely periods in the data. The triangle cursor above the curve can be dragged over the ellipse. When you release it, the graph on the right shows what the light curve looks like if we assume that period. Okay. Okay. Time. Oh, this is pretty complex. So it's taking the data of what we just did over there. So when you release it, the graph on the right shows what the light curve looks like. If we assume that if we assume that period, if you have many dips and can't find the period of the system, go back and take more data. Note that you can zoom in on the curve by clicking and dragging on the graph to define a zoom window. Or focus on it and press Z button. To bring the curve back to its original scale, click the zoom full button. Okay, zoom full. Okay. So I go like that. Oh, this is I think these are in days. Okay, zoom full shows the whole thing. Oh, okay. Okay, I get it. Nice. This is pretty complicated, but it's fun. So this one, I don't think we can, this is just a measurement. This is just how many data points we've taken. So I wonder how we can refresh the page. I think if you refresh, it will start again. Okay, so let's say if we did just measurements. Oh, you know what? If I press the let's see here. See, if I wait too long to press the cursor, then it's not taking as many data. So I could decide how often I want to click this. You see, I could decide. So I haven't clicked it. I should click it more often when I especially notice that it's going down. You see? No. Okay, that part. Going constant, going constant, going constant. Oh, this one is the intensity reading. You see, it's a full bar. Oh, oh, you see the light changes when it goes down. That means it's getting. I'm getting good at this, right? Yeah. Oh, there you go. Yeah. So when you see the light going down, then you take more data points. This is fun. It's like a video game. Okay, so then you go over here. Okay, so that's the full data that I took. I believe that's in days. Let me see that. Yeah, those are in days. Hold on. Yeah, those are time in days. So the triangle cursor above. So what is the period of this? How often is it dipping? Well, there's slight dips here, and there's dips here. So if you think the period, okay, hold on, let's zoom in on this. Period is 1.7 days. Well, I would like to measure the distance between one dip to another dip. So basically, I want to know intensity drops. Okay, let's just see here. Okay, let's go down to the actual exercise. Oh, there's just one question. Okay. Use the black hole system simulator above to determine the period for a black hole system. Make sure to take many measurements, especially when the intensity drops. On the analysis page, that the dips in data indicate possible values for the period. After choosing a candidate value of theta, make sure the intensity versus phase diagram for that value shows a nice clear dip. The intensity versus phase. After choosing a candidate value of theta, make sure the intensity versus phase diagram. Make sure that the intensity versus phase diagram for that value shows a nice clear dip. So I believe that should be the dip. It's a clear, nice dip. What if we were to clear this, focus on that more? But the problem is this data is kind of all over the place. You know what? If I go back to here, I can kind of estimate what my dip is. You see here, this graph goes up, then it goes down. So look at the dip from 22 point, each of this is 23 days, 23.4, no, this is 23 and a half days right there. So right now this is 22 point, yeah, so I think I'm going to use this to help me. Okay, I'm going to take a picture of this, I would say. Take a photo of that, zoomed in, and determine the distance between this dip and this dip and this dip and this dip in your mind, you know. So let's see, this is 25, 27 point, I would say this is 27 and a half right there, you see, and a half. So that would be 27.6 minus 25.1, maybe 25. So 27.6 minus 25.1, what would that be? 27.6 minus 25.1, 2.5. And then that should be the same as the dip from here to here. About 2.5, maybe 2.5. Okay, so the likely dip, therefore, from here is to be around 2.5, I believe. So that means this black hole is going around its companion every 2.5 days. Yep, 2.5 days. And it's hiding behind its companion every 2.5 days, which means its period is 2.5 days. So that when I go here, the likely dip that we're looking for is not 2. I need to full zoom now. Should be around 2.5. I'm not really sure what the theta is measuring. It might be measuring, and okay, let's go to 2.5 days. Oh, that's 3.25. Hold on, 2.5 is right here. Oh, right there. I think this is something else that they're measuring, theta versus time. It's not the dip. It's not the intensity dips. That's why that was confusing. This theta, it's probably measuring something else. We would have to look that up. But all of these dips are not the intensity dips. But what you're doing is you're saying, based on the graph that I have here, it's likely to be about 2.5. Then you go to 2.5. So then I'm going to focus in on this. So then you go to around 2.5. So I'm seeing right there, intensity dropped drastically. So you could take a photo of that and photo of it. Well, you could just take one photo even showing this whole thing, 2.45, and this is dipping. So that's likely to be the period. And there's probably margin of error here too. Oof, 2.45. Wow. Nice. But again, there's probably a margin of error. Try another version. Would it accept? No, there's too many dips here. No, it's not a clear dip. Those might just be, these might just be zoomed in versions of these. You see how these, there's slight changes. So that might be we're capturing slight changes in intensity, but let's see if it would accept that, you see. So 2.66. I don't think it will accept this. 2.09, but we could try. You want to let's try putting in the biggest looking dip here, but here it's not that good, you see. But I just want to try for trial's sake. Put in 2.13. Yeah, you see, I knew it. So it's not going to accept the theta dip. The theta is not the same as the intensity. So we have to look here more closer to here. And there's probably some range of values that are acceptable. Okay, so then take picture of that and then take a picture of that. Pretty interesting detection exercise. And I think with that, we are done. Cool. Great lab. Awesome. Okay, guys, thank you. See you later.